Greetings and welcome to a new video about another control system topics. In this video I would like to discuss how we can draw the Bode plot given a transfer function. So we have the transfer function. After several steps we will then have the Bode plot using the magnitude and also the phase. Of course we will carry out the calculation step by step and then verify these in MATLAB simulations. So let's look at our problem in great detail. We have now a system given which is GS and we would like to draw the Bode plot. This is GS. You can see we have two zeros, 0.1 and 40, and we have three poles at 2, 500 and also at 10,000. Now, what is the procedure for working out this and drawing the Bode plot? So the solution, first one is you rewrite your each term normalized to a low frequency gain of unity. So what does it mean? Let me rewrite this and see what we can discuss about this. We have now this 25,000. Each term here, you will actually get it out such that you have here a term plus 1. So we have actually this one will be then 0.1 will be converted to 1 by dividing by the 0.1. And you also divide this term. So you do that actually in a similar form for the second term for the 0 and also for the poles. So you will actually get out that 0.1, the 40, in this case 2, and the 500 and also 10,000. So you can see that in the blue for the zeros and for the poles in red. Now then you multiply these three scalar values and also for the poles in the denominator. So in effect you will get 10 to the power 5 here by doing 25,000 times 0.1 times 40. And in this case, you do 2 times 500 times 10,000, you will get 10 to the power 7. The next step is working out this. Now this can be, of course, written as 0.01 or 10 to the power minus 2. So this is actually what you have here in green. So everything is the same, and now we are actually done with step 1. Now, what you now do is determining your DC gain, if there is any, in this case there is, and your break frequencies. You can, of course, determine your break frequency already, but this is the nicer way to look at it and also draw the Bode plot later. So our DC gain, how we can determine that? Now, DC is determined as the frequency of 0 radians per second. So it means S must be 0. So if you substitute here for S equal to 0, for each of them you will get 1 times 1. And also 1 times 1 times 1, so you will actually get only 0.01. So this is, of course, the K value here. I just mentioned that as K for my DC value. This is scalar, but I need to move on to the dBs. That is how we use the gain in the Bode plots. So I have to use this formula. So I have to go from the K as a scalar to the K as dB as a unit. So it means then 20 log of that K. Now that means then 20 log of that 0.01. Now if you just calculate that, you will get minus 40 dB. Now we have a unit, which is then in dBs. Now the break frequencies. Break frequencies are we have two zeros. So 0, 1 at 0.1 radians per second. The other one at 40 radians per second. And we have three poles. Pole 1 at 2 radians per second. The other one at 500. And then the final one, the third one at 10,000. So we have now 5 break frequencies, and we will now use this in our drawing. Okay, the magnitude plot. For drawing your magnitude plot, for your Bode plot, we need to look at our lowest and our highest breakpoints. So in this case, you begin at least 1 decade before, and decade means actually 10 times smaller. So you will actually have your 0.1 radians per second as your smallest break frequency. So you start at 0.01, so 10 times smaller, and you extend your plot for magnitude also 1 decade above. So you actually go then, for example, in this case, the highest is then the 10 times 10 to the power 4. So you move up to 10 to the power 5, so 10 times larger, so 100,000. So in this case, we begin at 10 to the power minus 2, if we write it down in this form, and up to 10 to the power 5. That is now the plot. Okay. Now let's then look at the step 3. We first determine our slope for our magnitude plot. So what is the contribution for each pole and 0? So we have now the poles and the zeros here, so we have 2 zeros and 3 poles, actually in order from the lowest to highest frequency. Now I already have here the 1 decade below value and up to other frequencies. Now we know for a 0 that has a slope of increasing plus 20 dB per decade, and for the pole we have a decreasing slope, which is then minus 20 dB per decade. So that's actually what we need to remember for real zeros and real poles. For complex poles and zeros, the theory is a little bit different, but I will come back to that in a different video. So first, let's also determine the DC gain again. This is what we had, 40 dB. And then move on with the first one, which is 0, 1. In this case, we can say, okay, the 0, 1, which is then, we start with 0.01. The slope is there just 0 dB per decade, so it's actually before the actual location of your 0. Then it starts with 20 dB per decade, and it keeps that slope up to higher frequency. So this is just considering only one break frequency, which is then just 0, 1. If I move on and do the similar form for pole 1, which is the next break frequency, I have again starting at 0 dB per decade as a slope, because the actual action is at 2 radians per second, and still 0 dB per decade, and then it is now minus 20 dB per decade, and it keeps that slope up to higher frequencies. Again, this is only considering one break frequency at a time, so actually you do that in sort of a superposition principle. Now the 0, 2, again, I look at 40, so you can see actually 40, then it starts to increase by 20 dB per decade, and before it is just 0. In a similar form for 500, you can see it is now minus 20 dB per decade after starting at actually at 500 radians per second, similar for the 10,000. Now we need to now see what the total contribution is, because now we have seen each contribution. Now we need to also look at the total contribution. Now we add all those slopes, so for each column we just add them up, and then we get 0 dB per decade here, 20 dB per decade here, and then 0 dB again here, and here plus 20, and also here 0, because plus 20 is minus 20, plus 20, minus 20, and then 0, so you will actually add again to 0 dB per decade, and we have here minus 20 dB per decade. So we actually have here 1, 2, 3, 4, 5, 6 different slopes in our plot. So we will use that for the complete plot. So let's first bring up the plot, which is of course an empty plot. So we need to then draw our curve for our magnitude. So this is the magnitude in dBs, and this is our frequency again, extending from 10 to the power minus 2 up to 10 to the power 5. So it's actually 1 decade above and a decade below the break frequencies we have here. Okay, now let's move on and then draw the curve, first recognizing again the zeros and the poles. These are the pole frequencies. That's the next one, the 40 and the 500, and also the final one is 10,000. Okay, now the first one is actually here. So we have now here the zero of the slope is 0 dB per decade. What I need to be careful and also look at my DC gain. So I start actually at minus 40 dBs. So that's actually what you have here. So we start at minus 40 dBs. If this, for example, was 0 dBs, I need to make this flat line, which is then the slope at 0 dBs up to the frequency of 0.1. So this line, it's starting at low frequencies and up to 0.1 radians per second. It has a slope of 0 dBs per decade, and it's at a height of minus 40 dB. That's actually how you look at it. This is of course asymptotic, so in actual lines it will be more curvy and also a little bit smoother. Now the next one is 20 dBs per decade. That's actually from 0.1 up to 2 radians per second, so up to this line. So that's actually increasing line. So we can now have this increasing line. You can see from 10 to the power minus 1 up to 10 to the power 0, which is 1 decade above. I have an increase of minus 40 up to minus 20, which is then 20 dB. And then the same slope you will use, and then you will determine your value here. Now, this next one is the slope here, which is 0 dBs per decade, and it goes up to 40 radians per second. And you can see here what kind of value we have, which is minus 14. So you can calculate that this is 6 dBs again up. How can we do that? It is quite easy here, because 1 here, 10 to the power 0 is 1. You go from 1 radians per second to 2 radians per second, which is a doubling of your frequency. If you double your frequency and you have one real pole or 0, you will go up, if you have a 0, by 6 dBs per octave. An octave means actually you double your frequency. So you go from 2 to 4, from 4 to 8, and etc. So in this case, from 1 to 2, I can say it is minus 20, increasing that to minus 14. So add a 6 dB. Now, in a similar form for this slope, I already mentioned this, and then we go up again, but then from 40 to 500, so up to this line, so you can see that. And in a similar form, you just determine your slope so that you have exactly 20 dB per decade increasing, or 6 dB per octave increasing. Now, in this case, I get the next one, which is then 0 dBs per decade slope up to 10,000. And then from 10,000 up to higher frequencies, I need to have a minus 20 dB per decade. That's actually the next one. So this is just decreasing. This will keep decreasing. Of course, it doesn't stop there. Now we have this value of also minus 5 here. So it is again determined using this slope line and using your increasing line of plus 20 dB per decade or 6 dB per octave, depending on what is convenient there. Now, let's again mention the slopes here. This is then the 0 dB per decade segment. This is the second segment for 20 dB per decade, etc. actually for each segment here. And you can now also see this is actually for that part, this is for this part, this is for that part, this for this is for that, and the final one here. Now, this is how we can make it. Again, this is of course asymptotic, and if you draw this in actual, let's say in simulation, you will see there are curvy lines which are more smooth, and there are some deviations we will discuss later when we compare the simulations and also this drawing. So this is our magnitude plot in asymptotic format. Okay, now let's also look at the step 4, which is the phase slope contribution by each pole and each 0. So there we need more bookkeeping. So there are some more additional, let's say, steps we need to carry out. Again here, description giving the zeros and the poles. So we have 5 break frequencies. Again, we need to have the total slope. Then for the phase, of course, we start always for each break frequency 1 decade below, and we go up 1 decade above. So for example, 0.1 radians per second, I go down, 1 decade below, it's just 0.01, but I also go up 1 decade above, which is at 1 radians per second. So you can see starting for 0.1 and ending for 0.1. So you need to actually read that in this format. Now looking, for example, another break frequency, pole 1, it is at 2 radians per second. So I start at 0.2, that's the starting of pole 1, but I end at 20. That's actually what you see here. So 10 times smaller, 10 times larger. Again for the 40, 10 times smaller, 10 times larger. For the 500, 10 times smaller, 10 times larger, 5 kiloradians per second. Now for this one final also, the 10,000 will be then 10 times smaller, so 1 decade smaller, 1 decade larger, so it is then 100,000. So you can see we have then several frequency points where we now determine also the slope for each case. Now we know for the zeros that the increasing of the slope will be plus 45 degrees per decade. So you will actually have, starting at 45 degrees per decade, keeps that slope up to the 1 decade above this frequency, and then it has a slope which is then just 0. So it keeps increasing up to that frequency. The similar format also for this. So for that we just have only zeros. Now for that we only also starting here, so it's actually at 0.2, so it's 1 decade below starting, and also stops at 1 decade above. So you can see minus 45 degrees, because it is the pole, it will decrease, and for the 0 you will have an increase. In a similar form for the others, you can see it's starting, it's ending. In a similar form, it's starting here, the 500 radians per second, so at 50, and it stops at 5,000. Now in a similar form also for the final pole, pole 3, it starts at 1,000, but it stops at 100,000. Now we need to add all of these slopes. So these all 0, so where we don't see any numbers, it's just slope is 0, so you'll add them up. 45 degrees per decade, 0 degrees per decade, so just add them up. Add them up each column. Now we will bring up the plot for the phase. So we have the phases here of 180 degrees and also the frequency from 10 to the power minus 2 up to 10 to the power 5 radians per second. So we will now draw for each column here the segment for the phase plot and then generate the complete phase plot. So what we have then, again recognizing the zeros and the poles, so our break frequencies, these are of course important. And we have, of course, in addition, several other frequencies here to draw the segments. So first one is the 0.2, and then we have a line here, and then we will then draw for that part the slope, so increasing by plus 45 degrees per decade. That's the slope, and for the second one, it goes with a slope of 0 degrees per decade up to 1, so you can see it's 0.2 radians per second up to 1 radians per second. So that is the first, the second. The third one in a similar format, but then up to 4 radians per second, because it starts at 1 radians per second, goes to 4 radians per second with this slope. That is actually the meaning of this table. So you can see here the minus 45 degrees per decade. Now I have to be going from 4 to 20 radians per second, but then with a slope of 0 degrees per decade. Let me bring up my laser pointer. Now, this is then the line, and then we have now the 0 degrees per decade. In a similar form, you can do that for the next segments. So we have now 45 degrees per decade up to 50 radians per second. And from 50 radians per second up to 400 radians per second, you now have again a slope of 0. So, and that will keep plotting, so you can actually just plot this for each segment, and then you see, for example, here minus 90 degrees and minus 45 degrees up to the high frequency of 10 to the power 5 radians per second. But after that, the slope will be 0 degrees per decade. You can see that actually here, which is just, and that will go up to high frequencies, so it is not just ending there. Now the complete plot now is then this, without the arrows, etc. And of course this will be again a more smooth line when we have the simulation result, and we will compare that. Okay, let's now look at the simulation result and then compare what we have drawing. Now first, magnitude plot. This is our magnitude plot. We have seen this, and also you can recognize several things here. It starts really at minus 40 dBs, but it is not at minus 40 dBs for 0.1 radians per second, but it is at minus 37 degrees. And why that happens, I will describe shortly. Now, let's also look at the phase plot specifically. This is the phase, and you can see it is more curvy, more continuous, not like what we had drawn using asymptotic lines. And again, it has some lines here which has more slopes, but we will discuss this shortly when we compare that. Okay, now this is the complete plot for our Bode plot for this system. You can see several things again, and you can see also that the low frequency gain here, which is minus 40 dBs, and also at low frequencies the phase is approximately 0, so it's close to what we have drawn. And also for high frequencies, this gain will decrease, keep decreasing, but the phase will actually asymptotically approach minus 90 degrees. You can see that here. Okay, let's look at their line, what we have drawing, and also what we have from our simulation. This is the simulation. the top one. And this is our drawing asymptotically. So what recognizes the following: you have actually at the 0, you have 0.1, that is the radians per second, but it's still minus 40, but it says here that it is minus 37. That means there is some difference between the actual value and our asymptotic plot. The thing is, at the break frequencies, you actually have 3 dBs up for the zeros and 3 dBs down. So you go down actually at the break frequencies for the real poles. So that is now, that's the reason for not having minus 40, but minus 37 for this first zero. That's the same for this, because we had for this first pole minus 14 dBs per 14 dBs here, but it's actually lower, so it's minus 70, again 3 dBs lower. And again, it's the same for the other one, for the 40, because we had minus 14 there, it is minus 11, so it goes up because that's the second zero, so it will increase by 3 dBs, etc. So it's actually the same, similar form for the other break frequencies. So this, you can see, in general, the plot for the magnitude looks very similar to what we have determined. Of course, you need to also check the actual values, and that is indeed what we had. So it is here approximately 5 or 500 radians per second, and for 10,000 radians per second, it's approximately 5. So we have actually all those things very close to what we have in the simulation. So we can say this is correct. Now we can also move on to phase. This is the phase plot, and this is our drawing. Now again, it started 0 degrees in our case, but in this case it is starting at, let's say, at 5.5 approximately. Of course, if you go to lower frequencies, let's say 10 to the power minus 3, or maybe 10 to the power minus 6, almost to 0, this will approach 0. So this is just asymptotically for sure 0 degrees. Now we have now plus 45 degrees in our case for the first 0 part, but in this case it is a little bit smaller. That is due to the effect of curving again, and we have now 42 degrees here approximately. Same here 45 degrees approximately, very close to that. And this is also the case, approximately the case for our, in this case, for the pole 1. And in similar form you can see for the others. So in general you can see, and it is approaching minus 90 degrees as discussed before. So this is quite okay comparing with the simulations what we have drawing. Okay, that is then for this drawing. So that is actually the complete story about it, how you can generate the magnitude and also the phase plot in Bode plot using the procedure I have discussed in this video. There are of course other methods to do this. This is just one way to do the drawing of your Bode plot. If you have more complex systems, things will be of course more complicated, and you of course have to check the results more carefully. This is just the first example about using the transfer function from the Bode plot by only considering the real poles and the real zeros, and also have purposely chosen the zeros and the poles far apart such that they don't interact too much with each other, and then the slopes for the poles and the zeros, and also for in the case of the phases, are drawing much easily. We will discuss more examples concerning this topic, from transfer function into the Bode plot, which is important, and I will also discuss other variations like complex poles and complex zeros, etc., or a pole at the origin, or maybe a zero at the origin. So we will keep on working on that videos. If you have any questions about this, please let me know and I will try to answer them as soon as possible. Don't forget to like and share this video so that we can reach more people for this interesting topics. Thanks for your cooperation and see you next time. Take care.